Okay, good morning. Can everyone hear me? Does this work? Okay, hold on. Better? The same? Is that okay? Can people in the back hear me? Oh, okay, great. Thank you. Yeah. Yeah. So, hello. So welcome to the second day. You should all be able to see the homework 0 now. Sorry, there's a little mix-up in Gradescope, but I originally was going to be due Friday. I've extended it to Sunday due to the mix-up, but everybody should be able to see it. I shouldn't. It's just to practice LaTeX a little bit. I think everybody pretty much raised their hands, so everyone already pretty much knows it. It should take probably like an hour or so at most. It's just a couple of non-technical questions. Like I said last time, we're going to do this thing where we have 3 programming assignments, and I will release the programming assignment on next Monday, but the sign up is available now. So if you have teammates already, you can feel free to on Canvas. You just sign up yourself. I think it's under like people, and then you just move your name into a group. And if you have not signed up by next Monday, by the end of the day, we'll just assign everybody else who's left into random groups. After that point, the groups are final. So yeah, hopefully this reduces some confusion from last time. On Friday, there is a review session on using the cluster, which I think many people have not used, and more people have experience with C, C++, but if you're not super familiar, you might also find that helpful. There's a bit of an office hours time change, but they're all listed there, and they're all on Canvas. So there's like a calendar on Canvas, and I just put them there. So, yeah. And the homework 1 is going out right after class today. Any questions? All good? Cool. Okay, so today we are doing analysis pretty much of parallel algorithms. So last time we talked about why we are interested in doing parallel algorithms, and today we'll be talking about how do you measure how well your parallel algorithm uses the different parallel resources. So this is like we have a bunch of processors and we want to use them effectively. And so how are we going to measure whether or not we use them effectively? Okay. So they're based on traditional algorithm analysis measures that we already know. Like are people here already familiar with algorithms? Like, you know about big O, omega, theta? Yeah, so these are just traditional analysis measures for sequential algorithms, but we're going to use the same notation for parallel algorithms. And big O is, big O is like you have some function and it grows within constant of whatever function you're trying to bound it by. Omega is the opposite, which is like the lower bound, and then theta is both upper and lower bound within a constant factor. People already know that? Oh, okay. So let's go over it again. Big O is, if you have a function t of n is big O of g of n, that means t of n is always after some constant n sub 0. It means it's always less than some constant times g of n. So for example, 5n is O of n because like 5 is a constant, and in the limit it would be less than 5. Or like n is also O of n squared, like in the limit. So O is like a loose upper bound. Just any function can upper bound that, and also this omega is a loose lower bound. So like n squared is omega of n, because like it would grow much faster than n. But theta is like a constant factor upper and lower bound. So n squared is not theta of n, because there's no constant n sub 0 after which it would be bounded between 2 constants of n. People are getting that? Okay, yeah. So this is just what I said before. After some constant n sub 0, it's bounded within a constant factor of g of n. The lower bound is above some constant factor d of g of n, and then theta is just its O of g and omega of g, where g is another function. People good on this? Because we're going to use this going forward. All right. So if you remember last time, I told you that there are multiple kinds of parallel computers, but one main kind that every laptop or regular desktop nowadays is shared memory parallel computer, which means that it has this shared memory and multiple processors, and all the processors can access the shared memory. But the main point that we're interested in today is that there are many processors, and we want to take advantage of multiple processors. And all the processors can work independently and do separate computations. And then there's another kind, which is if you scale it up even more, there's distributed memory processors, which are just each of these processors are one of the shared memory processors. But from an analysis perspective, we just think of these as individual serial processors as well. And this is called a cluster, and this is the thing that you're going to do your homework on. It's called a cluster. They're connected by a network, and they can do communication between them. So the very high level way that we think about parallel algorithms is that normally, like in your traditional algorithms class, you have serial algorithms, which are like you execute one line of the algorithm at a time. In parallel algorithms, you just have independent, like you have those, but you can have many copies of them. So like they can execute different programs, they can execute the same program, repeat, like you could copy the same program, you could run the same program, but like different parts of it, whatever you want, you just have to tell your parallel computer who is working on what. Okay, and so these are two kinds of parallel computers. This is shared memory, and this is distributed memory. And we are parameterizing parallel algorithms by two things, n, which is the data size, and p, which is the processor size. So that's the main difference. Normally in like your regular algorithms class, you would just have, you would have t of n, which is like the amount of time that your algorithm would take. And here we have n, and we also have p, which is the number of processors that we have. So in these examples, p is equal to 6, because we have 6 processors. And it is clear that like for regular serial algorithms, p is just equal to 1. And we are not going to, ideally, we don't want to do worse with more p. Like p of n1 should be the upper bound on how fast we can do with a parallel algorithm. And yeah, so one question that we're going to answer today is, so we're going to use this to measure the parallel algorithm time, which is the time that the whole algorithm takes on p processors. So this might be less than t of n1. So if your algorithm took t of n, just in regular algorithms class, it might take some function of n and p with multiple processors. Okay. And the way that we measure how fast it's going to be, well, we have this runtime of the best sequential algorithm, which is ideally something that we learned before. This is nothing new that we're going to learn here. We already know sequential algorithms, hopefully. And the new thing here is that we are going to try to compute the runtime of the parallel algorithm, of a parallel algorithm as a function of p and n. And the speed up is just how much faster we got when we added more processors. So the speed up on p processors is just the serial time divided by the parallel time. So for example, if our serial time was 1 second and our parallel time was half a second, the speed up would be 2. And last time we talked about Anvell's law, which is a way to bound the possible amount of speed up you can get in a parallel program based on the serial fraction, which is how much of the program has to be done in serial. Does this make sense so far? We're good. And notice that the speed up usually, like for most fairness, we should base it on the best sequential algorithm, because often sequential algorithms can have access to optimizations that you can't do in parallel. And so it's not totally fair to compare, like you could run the parallel algorithm, but just on one processor. And that would be a fine thing to do. And that is something that you can calculate the speed up on, but often it will be worse than the best sequential algorithm. And so like sometimes there's this like uncomfortable truth where you draw a speed up plot and like your scaling looks really good with processors. It looks like you grew proportional, like the speed dropped proportional to the number of processors. But maybe if you draw the serial time, which is like a flat line, it is similar to what you got at some number of processors greater than 1. Like maybe your best serial time was comparable to 8 processors or something. Yeah. So speed up is this serial time divided by parallel time. And that's something we're going to calculate in the theoretical sense today, but in the homework and when you actually run your programs, that's something that you calculate just by running the program. Like you run it on one processor, you run it on P processors, and you divide. And you can draw a plot. So like the x-axis would be number of processors, the y-axis could be speed up. Or the y-axis, if it's speed up, you hope it goes up and to the right. If it's time, you hope it goes down and to the right. Okay. The speed up, in the theoretical sense, is bounded above by p, which is the number of processors that we have. And does that kind of make intuitive sense, people? Like that you can't do better than p speed up. And the reason is like the proof is pretty simple, which is that we're going to show it by contradiction. Suppose that you could get a speed up greater than p. And remember that the speed up is the best serial algorithm time divided by the parallel time. And so we just plugged in the definition of speed up, it's greater than p, and then we just multiply this parallel time on both sides. So we got the serial time is more than p times the parallel time. But we had assumed in the beginning that that was the best sequential algorithm. And however, we could get a better sequential algorithm through this thing that we just showed. So we had the original serial algorithm that we had was slower than p times parallel time. And so we can make a new sequential algorithm by just taking the parallel algorithm that we had and running it on one processor, just in serial. And we had p processors. If you run it on one processor, ideally that should take no more than p times the parallel time. And so using this, we can get a new, better sequential algorithm that runs faster than the original one that we had assumed, but that contradicts our original assumption. So that's the end of that. And you can always simulate a serial algorithm on a parallel algorithm, or you can always simulate a serial algorithm with a parallel algorithm by just running it on one processor. You just, like different processors are doing different things. You just do what was processor 1 doing, and then what was processor 2 doing, and so on, up until the end. In a theoretical sense, speed up is always bounded above by number of processors. And that's also that's kind of how last time we were talking about calculating peak. That's kind of like one way to think about how you would calculate peak. Like if you have two processors and they run at 2 gigahertz, in total you cannot do more than 4 gigahertz. Okay. Practically, sometimes you can get more speed up than p. This is just like a small side note. Sometimes, in rare cases, you can get it's called superlinear speed up, which is that you get speed up more than p. And the reason is that sometimes when you get more processors, usually you also get more memory or cache, and you can have better cache effects. Like if your data doesn't really grow, if your data grows less than your cache grows, then maybe you could fit more of it into cache, something like that. And you can access it faster. But in theory, like when we're proving things about speed up, we can only get up to p at most. People good so far? Any questions? Yeah. Yeah, this is just a practical thing. So for example, like let's say in serial, we were just using C0, core 0. And then now in parallel, like we use 4 cores. So we're going to use C0, C1, C2, C3. And then we're also, originally we got access to L1 and L2 only here. But when we use the multiple cores, we may get access to all of these L1 and all of these L2, which are local to each core. And suppose that our data set did not grow. Like suppose that our data set could not fit into just one L1 and L2, but it could fit into 4 L1 and L2s. Now we can access them faster because they fit into higher levels of cache. Yeah. That makes sense? But this is like, we don't really have great models for the intersection between parallelism and caching. And so it's mostly just a practical thing. Good question. Any others? Okay. Yeah, So now we're going to use speed up to introduce another measure, which is called efficiency. And efficiency is just, it's very related to speed up. It's just how well we are using the resources of the computer. So the gold standard for parallel algorithms is called work efficient parallel algorithms. And that means that it does no more than a constant factor of work than the best sequential algorithm. So like if the best sequential algorithm took linear time, like order n, we don't want the parallel algorithm to take like n log n or n squared or something like that, ideally. Like even if you had infinitely many processors, that would you still might be slower because depending on how the parallelism worked. And in reality, we don't have infinitely many processors. So as the problem size grows, the difference in the function will grow faster than the number of processors that you can keep adding. So ideally, we want work efficient parallel algorithms, and efficiency means the work done by the best sequential algorithm divided by the work done by the parallel algorithm. And work is just the work is like the time. So like what you would normally measure in an algorithms class, like the work of sorting is like n log n, for example. So it's just like time. And the work done by the parallel algorithm is also the parallel time. And the speed up and the efficiency is serial time divided by p times parallel time. Because in some sense, p times parallel time is like the volume of work that the parallel algorithm did. And notice that this thing, serial time divided by parallel time, is the speed up. So it's just speed up divided by p. And we just said that speed up is bounded above by p, so this thing can be at most 1. Yes? I see. Yes. Thank you. The question was like, is work done by the parallel algorithm, is it parallel time, or is it like the volume of work done by the parallel algorithm? Yes, it is the volume because it's p times the parallel time. So it's like if you had concatenated all the parallel times together on one processor. Thank you. Yeah, so this is the actual time. This is the actual parallel time, TNP, and this p times TNP is the volume of parallel work that we're doing. So like in the example that we had, if the serial algorithm takes 1 second and you had 2 processors and it takes half a second, then efficiency would be 1. It's like 1 divided by 2 times half. Yeah. And yes. Sorry, could you say the second half again? Oh, so the question is like, why would you? So if you know that, like for example, your program is 20% sequential and 80% parallel, why would you be interested in this efficiency measure? One thing is that sometimes it is hard to calculate what fraction of your sometimes it's hard to calculate the fraction of how much your code is serial and how much your code is parallel, because like when you could like how would you measure that? You count the time, you can count the lines. Both are not really perfect measurements. And also, yeah, so efficiency is easier because it just depends on the times, which is something that we can easily measure. Does that answer your question? Good. Any others? Yes. Can't they just, why does it, question is, why does it matter what your parallel algorithm is? It could be different from your parallel algorithm. It could be the same as your parallel algorithm. Yeah, so maybe I didn't understand the question, so maybe I can try to repeat it. Why would you be interested in efficiency if the sequential and parallel algorithm are separate? You would still be interested in, I think, because efficiency is just a measure of how well your parallel algorithm is making use of the resources. So if this thing is very low, then that means like it's not really worth using your parallel algorithm because you already have a good sequential algorithm for the problem. Thank you. So yeah, so from a practical standpoint, if you think about how you would plot efficiency, you would measure this sequential time, which is you just run your program and you measure the time. You would run your program on you would run your parallel program on P processors, and then you would divide them and you would divide the whole thing by P. So in an ideal world, your efficiency plot is just a flat line at 1. In reality, it's not usually kind of drops off a little bit, but in a perfect world, it would be flat at 1, which means that we're using the parallel resources as much as possible. Yes. How do you determine what is the best sequential algorithm? You can prove lower bounds on sequential algorithms sometimes. Like, we still have algorithmic lower bounds, and if your sequential algorithm meets the lower bound, that is one way to determine best. From a practical standpoint, you could just run all your sequential algorithms and pick the best one. Good question. Yeah. And this might be like from a practical standpoint, this might be so like in theory, you could ignore the constant factors, but when you actually run the code, sometimes the constant factors will actually show up in the time, and so you may consider ones that have lower constant factors as well. But for work efficiency, we only care about a constant factor in the work. Everyone good? Okay. Yeah, so that's efficiency, which is just the speed up divided by P. Okay, so let's go through an example. We will go through this example many times in the class, but we're going to do matrix multiplication. And for matrix multiplication, for simplicity, let's just assume they're square. And the algorithm to do matrix multiplication is just this 3-loop version. We go over I, we go over j, we go over k. K is the fastest moving dimension. And for every entry of the output matrix C, we go over 1 row of A and 1 column of B. And we do like a dot product between the row and the column. Yeah. So what is the serial work of this algorithm? How many steps is it going to take? Thank you. Yes, good. Yeah, exactly. So on one processor, we have the input length is n. We have one processor that's theta of n cubed. So suppose we had these 2 parallel algorithms for matrix multiplication. Parallel algorithm 1, the input size is always n. If on n cubed processors, it's going to take log n time. And then parallel algorithm 2, on n squared processors, it's going to take n time. Okay, so we want to compare them. We're going to use the measures that we just talked about. So first, we want to calculate speed up. Yeah, so again, I just repeat this. On n cubed processors, alg1 takes log n, theta log n time. On n squared processors, alg2 takes theta n time. And the speed up, so remember that the speed up is the serial time divided by the parallel time. And what is the speed up? N cubed over log n. And why is it important that they were both theta? You're comparing the two. Can you say more? Yes, good. Yeah, so really good point. It's important that it's theta because if something is big O of something else, it may not be strictly a constant factor of that thing. It just has to be less. So dividing big O's will not necessarily give you something else that is also big O of that thing. And that just comes from the definition of big O that we had in the beginning. And on your own, you can provide a counterexample in the vein that I just gave, which is like, if 2 things are big O of something and you divide them, they may not be big O of the divided thing. they will be if they're theta. So that's why it's important that they're theta. Yeah. Yeah, so this is what I just said. If you divide them, it may not be big O of that thing. Okay, so the speed up is we just divided the serial time over the parallel time. That's n cubed divided by log n. And then the efficiency. Sorry? Yeah, so p is n cubed. Yeah, it would be 1 over log n because we would just divide this thing by n cubed. Yeah, so n cubed in the bottom gives us theta 1 over log n. And then we're going to do the same thing for algorithm 2. So the speed up is the serial time divided by the parallel time. That is n squared. Yeah, should be. And then efficiency is, that is this thing divided by the number of processors. So that's n squared divided by n squared, which is 1. Questions? Okay, and remember that we wanted efficiency to be as close as possible to 1. Okay. Yeah, so we want efficiency to be as close as possible to 1, but on the other hand, we want speed up to be as high as possible as well. So how should we determine which one we should aim for, speed up or efficiency? And you can see here, like these are not necessarily, they don't necessarily line up exactly, because here speed, this thing n cubed over log n is higher than n squared. Okay. And one way that we're going to resolve this is through another short lemma called Brent's lemma. And what Brent's lemma says is, suppose we have a parallel algorithm, P n p sub 1 is the runtime of this algorithm designed to run on p sub 1 processors. We can simulate this algorithm on p sub 2 processors less than p sub 1 processors. And if we do that, we're not going to lose any efficiency. So for any number p sub 2 less than p sub 1 processors, the efficiency is going to be equal to the efficiency on the max number of processors that it was designed to run on. Sometimes it's called efficiency scaling. And then one thing to notice about this is it does not say that the algorithm is efficient. It just says it's going to match the efficiency on the max number of processors that it was designed for. So if it was inefficient on, like in the previous example, like n cubed processors, it's going to be inefficient on any number less than that. And the way to prove this is kind of similar to the other proof that we did. There we simulated p processors on one processor. Here we're going to simulate P2 processors on, we're going to simulate P1 processors on P2 processors. We're going to simulate the higher number on fewer processors. And the way to do that is, remember that P2 is smaller, so we're just going to have each one do this amount of processors. Like the greater number divided by the lower number, and then the way we're going to do that is like the same as when we were simulating on one. We just keep running, like sequentially, the processors work. And so the parallel time on P2 processors is just this simulated constant. This thing is greater than 1 times the parallel time on P1 processors. So if you have fewer processors, the time should increase. But if you plug it into the efficiency formula, here, serial time divided by number of processors times parallel time, then we just plug in parallel time this thing here, and we get out the expression for efficiency on the higher number of processors, P sub 1. Does that make sense? Mm-hmm. This one? Yeah. So we have the first line because we were simulating, we had an algorithm that runs on P sub 1 processors. But in reality, we have a smaller number, P sub 2 processors. And we're going to use each of those P sub 2 processors to run several of the P sub 1 processors in a logical sense. So like say we had 4 processors, say we have like an algorithm that can run that we know runs on 8 processors, and we only have 4. So each of those 4 would run like the work of 2 of them. We would just run 1 and 2, one after the other. That makes sense? Thank you. Yeah. Mhm. Oh, yeah. So we're interested in the simulation because we may not have P1 processors. Like in the previous examples, like here that was n cubed and n squared. Often we probably won't have n cubed or n squared processors for large enough n. Good point. Thank you. Yeah. So if you did have this many processors, like you wouldn't, exactly the point, like you wouldn't need to simulate on fewer processors. But we'll get to it a little bit later, which is like if as n grows, you probably don't have n cubed processors. But it's okay because with Brent's lemma, you maintain the efficiency with fewer processors. Thanks. Yeah. Okay. So going back to this question, which is we have speed up and efficiency, which seem to be 2 competing metrics sometimes, and which one should we care about more? So let's go back to this thing. We had 2 algorithms. One can run on n squared, one can run on n cubed processors. And in reality, and let's say we have 2 processors, in reality, even n squared is usually much more than p. So think about a normal size matrix multiplication, like even like 100,000 by 100,000, or like, I don't know, even a small one like 1,000 by 1,000 on your normal multi-core machine, like you don't have 1,000 squared cores. Even 100 by 100, you don't have 100 squared cores usually. Like you shouldn't need a huge distributed computer to multiply 2 matrices of 100 by 100. So that's why we want to do the simulation. Yeah, so remember that we have these 2 algorithms. This one runs on n squared processors and takes time n. This one runs on n cubed processors and takes time log n. And remember that we wanted work efficient algorithms. And the way that we can compute the work is to do the processor time product. So this is kind of what we were doing in the efficiency below. Like, remember in the lower part of efficiency, it's p times parallel time. So this is just p times parallel time. Yeah, and that's the volume of work. So this would be log n times n cubed. And this would be n squared times n. Yeah, and on p processors, this is just n squared over p and n cubed over p, number of processors. So in general, the goals of designing efficient parallel algorithms, for speed up, we want to minimize the parallel time using the smallest possible value p. And then for efficiency, we also want to maximize the efficiency for maximum possible p. Because of Brent's lemma, if it's efficient on a large number of processors, it will be efficient on any smaller number of processors. And in general, to design fast parallel algorithms, we should target efficiency. And because efficiency will give us speed up on the range of processors that it's guaranteed on. Because if you remember, like the relationship between efficiency and speed up, efficiency is just speed up divided by p. Mm-hmm. Mm-hmm. I see. Yeah, so the question is, why can we do the simulation? We can simulate more processors with fewer processors. We cannot simulate fewer. Not sure why you would want to simulate fewer processors with more processors. It's just so the reasoning behind efficiency is like the reason behind maximizing P for your efficiency statement is because of Brent's lemma that we just showed. Brent's lemma is saying if you have like a theoretical bound for more processors and you run with truly fewer processors, then it will still achieve the same efficiency. So the simulation is going in the direction that you have fewer processors and you want to simulate more processors. So maybe the confusion is that the direction of the simulation is wrong. Yeah. Yeah, so here, like maybe simulation is too strong a word for what we're doing. We're just running the work of multiple processors on one processor in serial. So like simulating is just like you're just doing what you would do with multiple processors, but like since you don't have so many, you just kind of like pretend that one of them is many of them. Yeah. So like maybe there's a constant overhead to determining that, but it's pretty small. Maybe going back to this question. So let's go back to this. Yeah, so for Brent's lemma, this is saying that if you have P sub 1 processors and you actually are running on P sub 2 less than P sub 1, you're going to match the efficiency. Mhm. Oh, the question is like, if you have fewer processors, why does the runtime scale proportionally to the number of processors? Oh, I see. Because assuming that you have P, so like this is just the same thing that we did here. Like that we had, you have a higher number of processors, and you want to simulate it on a fewer number of processors. Like in the example that I was giving, you have 8 processors. Theoretically, you can use up to 8, but you have only 4. So like processor 1 needs to run the job of processor 1 and 2 serially. And so that is assuming that they all take like the same volume or length that is going to give us this expression. That makes sense? And so same for this, we just plugged in n cubed as P1 and P as P2. Did I answer your question? Thank you. Yeah. Anything else on this part? Okay. Yeah, so the main part to remember here is that we want to, oh yeah, please go ahead. This thing? Yeah. So this thing is just so if we go back to here, does this part make sense? So that thing is just using concrete numbers for P1 and P2. So in the next example, like this is the real number of processors that we have P. So here, the time that it takes to run on P processors is the time on the max number of processors. This is time on P1 processors. This is P1, and this is P2. So we just plugged in the actual numbers there. Mm-hmm. Thanks. Really good question. So one main thing to remember is that we want to design efficient algorithms. And efficient means that we don't want to do more than a constant factor of work compared to the serial algorithm. And this one is not work efficient because we have n cubed processors. Each one is taking log n. So the total volume of work is n cubed log n. But we just said that the serial algorithm is n cubed. So this is more than a constant factor of the serial algorithm. Questions? All good so far? Yes. Why are we using the smallest value of P for the speed up? Because if we, like in the previous example, this P that it could use is much larger, but it came at the cost of efficiency here. So I guess there's two reasons. One is that maybe multiple reasons, but one practical reason is that if you can guarantee speed up on smaller possible values of p, you can achieve the speed up on a wider range of machines. From a theoretical standpoint, you want to minimize this. I don't know. I think it's fine maybe from a theoretical standpoint to use bigger p, but I think from a realistic standpoint, you want to use smaller p. Mm-hmm. Yeah. So go back. Okay, yeah. So here we want to design work-efficient parallel algorithms. And work-efficient means that the parallel algorithm does no more than a constant vector of work compared to the sequential algorithm. But here, we can just go here actually. Yeah, okay. So here, we need parallel algorithm 1, and it runs on n cube processors, and it takes log n time on each. And the total work, which is like the volume of computation, is n cubed times log n. And so that is not work efficient because the serial algorithm was n cubed. Mm-hmm. So we're targeting for efficiency because, well, speed up and efficiency are very related. If you get good efficiency on many processors, you would also get good speed up because like efficiency is just speed up divided by p. So if your efficiency was 1 for a large range of processors, your speed up would also be like p. So that's just to say like you shouldn't explicitly target speed up in algorithm design. Like here, this was targeting speed up, but it gave up efficiency in the process. But if you can achieve speed up on a large range of good efficiency on a large range of processes, like n squared is quite a large number of processes, then this will give you also good speed up because efficiency is just speed up divided by p. Mm-hmm. Thank you. Yeah. Okay, yeah. So like I was saying, the work is the processor time product. For algorithm 1, this was not efficient because it's n cubed times log n. For algorithm 2, it was efficient because n squared times n is n cubed. So it matches the serial algorithm bound. And suppose that we had a third parallel algorithm that runs on n processors and takes n squared time on n processors. And now both of these algorithms, 2 and 3, are efficient because n times n squared is also n cubed. And so next we're going to talk about how can you choose between these two efficient algorithms. And I kind of already said it before, but you want to maximize the number of processors that you can use in a theoretical sense, because even if in reality you have fewer, you will still you'll still match the efficiency on fewer processors if you have a bound for more processors. Yeah, so one way to formalize this is some notion called fixed time scalability, which is fixed time scalability is a type of scalability, which is like if you increase the resources, if you increase the problem and you increase the resources to match the problem size, how does the runtime change? And ideally, if your problem size increases and your resources increase by the same amount, or the same factor, ideally you would like the time to stay fixed. That's why it's called fixed time scalability. Okay. So this is an ideal efficient algorithm, which is that we have n cubed processors, and each one takes order 1 time. Ideally, it doesn't exist, but we would like to have it because this is efficient. It's n cubed times 1, and it uses the maximum possible number of processors that we could possibly, like the volume of work is n cubed. Doesn't make any sense to have more than n cubed processors, because like then you would have more processors than actual computation steps you need to do. Okay. So the parallel time on p processors is n cubed over p. And this is just plugging in, like p sub 1 is n cubed and p sub 2 is p. So plugging into Brent's lemma, for any p less than n cubed, we would get this time. And so we're going to try to calculate fixed time scalability. We increase the problem size by 2, so n is doubled. The work is increasing 8 times because the work is proportional to n cubed. So like 2n cubed is 8n cubed. And then, so the work increased by 8 times, so we want to increase the processors also by 8 times to grow proportionally to the work. And so the work is, the length grows by 2, the processors grows by 8, and then 8 and 8 are both here, and we end up with n cubed over p again, which is what we want. The time did not change when we grew the work volume and the processors proportionally. But here, on the other side, if we look at this inefficient algorithm that we had, so we had n cubed processors, we have log n parallel time, and we do the same thing. We increase the problem size by 2, we increase the processors by 8. Now this thing is n cubed log 2n over p. And previously, the parallel time was n cubed log n over p. So this thing is growing, even though we increased the problem size and the processors proportionally. So that's another way to see like why we would want efficient algorithms. In this case, it is also theta. Yeah. It is theta. Theta implies big O. But yes, these can all be replaced by theta. Like theta means that something is big O of something and omega of something. But it's not the other way around, like omega or big O does not imply theta unless they're both together. Yeah, these could be all theta. Questions on this part? Yes. For here, we're only considering processors. Like right now, we only have P, which is the number of processors that is going to show up in the bound. Later on, we're going to talk about how memory affects, how like we can theoretically analyze the memory usage. But the problem is that like we don't have really good theoretical models for combining memory and processors. So usually, like theoretically, people just consider both of them separately. But for now, we're only considering processors and how well we can use them. Yeah. So we have this example of 2 efficient algorithms, n squared. One uses n squared processors and takes n time. One uses n processors and takes n squared time. And in general, when you have 2 efficient algorithms, you want to use the one that can use more processors. Because in this one, if you increase the number of processors by 4, then by 4 times, then the runtime only increases by 2. But here, if you increase the number of processors by 2, then the runtime would increase by 4 times. Because this thing grows with n, this thing grows with n squared, and vice versa in algorithm 1 or algorithm 2. Yeah. And so we can do some concrete examples. Suppose we're doing 2 1,000 by 1,000 matrix multiplications. So n is equal to 1,000, and suppose that we have p equal to 100 processors. So p sub 2, which is the maximum number of algorithm or maximum number of processors that algorithm 2 can use, is 100 squared. No, sorry, 1,000 squared. And then the maximum number of processors that algorithm 3 can use is n, so it's 1,000. So this is just fine for now because we have number processors 100, which is less than both of these. So it would be efficient in this case on both, like both algorithms would still be fine in this case for p equals 100. So now suppose that we double the problem size, we get 2000, n is now 2000. The work increased by 8, so we want to multiply the number of processors by 8 to try to keep the runtime the same. And now p is equal to 800, p3 is equal to 2000, which is the max number of processors that algorithm 3 can use, and p2 is equal to 4 million. And so in this case, we can still use either algorithm because the number of processors that we actually have is less than the maximum number of processors that the algorithm is guaranteed to be efficient up to. But if you double it again, now say we have 6400 processors, algorithm 3 is not guaranteed to be efficient on this because algorithm 3 is only guaranteed to be efficient up to 4000 processors. But however, algorithm 2 can use many more, and so that's why you would prefer the algorithm that can use more processors, but is still efficient. So to summarize this part, when we have parallel algorithms, we have two main criteria. First is to maximize the efficiency, and second is to, if you have two efficient algorithms, pick the one that can use more processors. Questions? Okay. So next we'll do some more examples. So suppose that we want to add up numbers in an array. It's like a basic problem. We have n numbers. We want to compute their sum using p processors. And suppose in this example, p is less than n. We have 12 numbers and we have 4 processors. So this is like what a lot of parallel algorithms look like. You do a serial part, which is some local computation, and then you do a parallel part to combine the answer. So in serial, everybody has n over p numbers. So n was 12, p is 4, so n over p is 3. Everybody has 3 numbers. You add them up locally, and then you get some local sum, and now you need to combine them. And the way that we're going to combine them is in this tree-like fashion. So in the beginning, these two pairs, this pair, and this pair add up their numbers together, here and here. And let's say that now this one resides here, this one resides here. Now these two combine their numbers to get the total sum. What is the serial time and what is the parallel time? Okay, the serial time is order n because it took up n time, it takes n time to do the summation. Like if you just had one processor, you just add them up left to right. To calculate the processor, or to calculate the parallel time, there are two parts. One is that we're going to calculate everybody's local sum, and then we have to combine them together. So the first part, how long is it going to take to add them up locally? It's a question. It should be a function of n and p, p processors. Yes, good. So that's n over p. And the second part, what is the height of this tree? Log p, yes. Does that make sense? Because there's p processors, or there's p leaves in this tree, and then so the height is log p. So the parallel runtime, you just add them together. N over p plus log p. Is this clear to everyone why the height is log p? Good. Then this one is just, we just evenly divided the work n over p. Like, why is it not log base 2? Yeah, so it's just in the theta. And so we want to find p to minimize the parallel time. And we can do that by taking this derivative, and we can find that p is equal to n. So the minimum parallel time is p equals to n. This is negative n squared over n over p squared. This part becomes 1 over p, and this thing just moves over to that side, and then you multiply. Okay. And then we also want to maximize the number of processors for which this thing is efficient. By efficient, I mean theta 1. And so we plug in this definition of efficiency, serial time divided by p times the parallel time. We want this to be theta 1. And we have the serial time, that was n. We have the parallel time. We just computed that, n over p plus log p. And then we get n over n plus p log p in the bottom. And so this whole thing is going to be theta 1 if p log p is order n. Yeah. Because then this just going to be like 2n in the bottom. And we're going to figure it out. We want p log p equals to order n. And we prove it by substitution that p is order n over log n. So if we guess p is order n over log n, you just plug in p in this expression here. We want to figure out p log p. So this is p is equal to n over log n. We plug it in for p here. And then we get order n. So this is n over log n times log of quantity n over log n. The thing on the left, this is like log rules. Division inside becomes subtraction. And then in the big O notation, this thing goes away. This is n over log n times log n, and this is order n. Just smart guessing.
It seems you prove your theory was based on 100% that gas. Then how to weigh make sure our gas
We can probably try different. So this is like p log p, and then here we had n over log n. So the things that we will see here probably are just similar to this, maybe with different log factors, like log squared or something. And so you could try n over different factors of log in the denominator. It's probably more complicated than something that will be in the exam. I don't know. It will be. This is like something that you have to guess. If it would be something like this in the exam, I would give like multiple choices, and then you could try them. Question. Any questions on that part? Okay. So this is the last part, which is we're going to talk a little bit about how we're going to model communication, which is kind of related to your question of memory. So we don't have great models for how to like model caching and parallelism, but we do have models for how to combine communication, which is like sending data and parallelism. So let's go back to the example of parallel sum. We have these leaves in the parallel sum, and we combine them in this tree-like fashion. So we just computed the serial and parallel runtime, which was n. And then here in this example, we just have p equal to n. So the parallel runtime is log p also. Here p is equal to n, so log p is log n. Then the speed up is serial time divided by parallel time. And that is n over log n. So the speedup is bounded above by n over log n. And n is the maximum number of processors that we would reasonably want to use for this problem because we only have n numbers, so it doesn't really make sense to have more than n processors. Okay, so let's look at an example. Suppose we had 1,000,000 numbers that we wanted to add up. Speedup is bounded above by n over log n. We have 1,000,000 numbers. Log n is about 20, and the speedup is bounded above by 50,000, which sounds good until you remember that we had 1,000,000 processors, and so that was 5% of the number of processors that we had. And in reality, we have multiple processors connected by some bus, which is like a hardware thing. And to transfer data across the bus, which is something that we need to do this tree summation, like, yeah, so this part, when we need to add these two numbers, if these two numbers are in different processors, P1 would need to send A1 to P0 for P0 to add up A1 and A0. And so it needs to incur the cost to transfer this data here over the bus. And the same issue for all of them, like this one here, that one there, that one there. And then again, like at the next level, we would need to send this one here to P0. And the way that we model that in theory is through this tau factor. And tau is the transfer latency, is the factor of transfer latency relative to the compute speed. So in the theoretical model, compute speed is like order 1, which is to do any operation. And tau is relatively how long it takes to transfer 1 unit of data, like a byte. And unfortunately, the transfer latency is usually on the order of 10,000 slower than compute. And we kind of saw that in the first lecture, like this gap between memory and processing. Okay, so now we add this tau factor into the parallel runtime. So for the entire first part of this, we were not considering any communication. We're just considering computation and how well the computation can use the multiple parallel processors. And that is something important also. But for more fine-grained understanding of how this will actually work, we should include other factors like the communication cost, because that is something that the parallel algorithm needs to incur, but the serial algorithm does not. Because like the serial algorithm would just hold all the numbers on one processor and add them up using compute steps. So that's something that only parallel algorithms need to do. And so the serial runtime is 1 times n, because it's like only compute and it does n steps. You just add them up. Parallel runtime is tau times log n, because there are log n levels in this tree, and each of them needs to incur tau transfer latency. The transfer latency can happen in parallel. Like all of these transfers happen in parallel, and each of them takes tau. But we're not adding them up because they can all happen in parallel. But they need to incur at least tau because at least one transfer is happening. Okay, so using this previous example with 1,000,000 numbers and tau is 10,000, now the speed up is even sadder, it's like 5, because we had serial time divided by parallel time, but parallel time now has this communication cost involved in it. And so this is like an important point in parallel algorithms, which is sometimes the issue is not how many parallel processors you have. Sometimes the issue is the cost of communicating between them in many cases. So often speed up, like here, the issue was not that we didn't have enough processors. The issue was that the communication time was too high relative to the serial time. And that's why the speed up is very low. Okay, so how can we improve the speed up? decrease time. In the algorithm side. Yeah, good point. Yes. Transfer as much data as possible when we're doing the transfer. Can you say more? Being efficient with your data transfer. So like here, how would you reduce the data transfer or like be more efficient with it? You can change the algorithm. It doesn't have to be. It could be. You can still use the tree. It could be like kind of like a tree. Um, I see. So we can maybe try to use an SMP, but also in SMP, sometimes you have an issue of like different processors have different local caches as well. But this, let's just, since we're modeling communication, we should stick to distributed memory for now, because usually this tau factors in like distributed memory models.
One sum per communication. Since again, communication is really
Yes, very good. So yeah, exactly. This is kind of what we were doing in the beginning, but it's now we're going to do it in a more rigorous way. So this is what we had in the beginning. We have P processors, give n numbers, and we want to sum up numbers locally as much as possible in each processor before doing this, and that's how we're going to reduce the depth of this tree. It goes from log n to log p. Yeah, and now we can calculate the serial and parallel runtime using this type of algorithm. So this is like maybe something to remember when you design parallel algorithms, which is like, because communication is an issue, you want to do as much as possible as you can locally, because compute is much faster than data transfer. And then only when you need to, you transfer data. And we do have to still transfer data, because this is assuming that not all the numbers can fit in a single, well, to do parallel processing, you wouldn't want to fit all the numbers in a single processor, because then the other processors would be standing idle. Okay, so the serial runtime is n. Yes. Sorry. Yeah. Could you send all the data? So like everybody would receive this data here. You could, but then you would have to queue up the communications. And so like the reason that previously we had tau at each level was because all the communications were happening in parallel. But assuming that tau is the startup cost of any processor receiving any other processor, then we would have to incur tau every time somebody sends to us. Yes. Yes, but that level would now cost 4 tau. Or I guess 3 tau, because it's like 1, 2, 3 sending. So tau is like the startup cost of any processor sending to any other processor. If the two endpoints are different, then you have to incur tau again. So like process 2 sending to process 1 counts as tau. Process 3 sending to process 1 also counts as tau. So yeah, so ideally, it's a good idea, which is like the idea is good, which is like you want to maximize the amount of local computation. And the way that you would do that is to send everybody. But because of the way that the data transfer works, you also want to try to parallelize the data transfer as much as possible. Yeah, okay, so serial runtime is n, parallel runtime is n over p plus tau log p. So n over p is this local summation, tau log p is the data transfer part, and then the speed up, you divide them, and serial over parallel time, n over p plus tau log p. And yeah, using this previous example, if n is 1,000,000, p log p, yeah, so p log p is less than n. Because this is the maximum number of processors for which this is efficient. So n over tau is approximately 100, so p is at most 22. So maybe the moral of the story is, for something simple-ish, like summation, you don't need so many processors to make it efficient. Like 22 is obviously much less than 1,000,000. Yeah. So that's what we were just talking about. We have these different processors. They're connected by this interconnect for distributed memory, and each of them has a local memory. Yeah. So when we model memory transfer, there's two costs. There's latency, which is the startup cost to transfer that we just talked about, that's tau. And then there's bandwidth, which is the average rate at which bytes transfer over the network. So like when you have a bus, people will tell you like, oh, it's, I don't know, 5 gigabits a second, for example. And that's the bandwidth. So you can think of it as this analogy, like bandwidth is throughput and latency is just the delay travel time. So like low bandwidth means that not many things can go through at a time. High bandwidth means a lot of things can move through at a time. But latency doesn't depend on the amount of things that you're sending. Like whether you send 1 byte or 1,000 bytes, the first one still has to incur that latency. But the more data you send, the more that bandwidth starts to matter. Yeah, so all that's here is pretty much that the transfer time, if you're sending a message of m bytes, transferring that message will take you tau plus mu m. So tau is the startup cost of the latency, mu is the bandwidth, and m is the number of bytes. And so for small m, like if m was 1, tau is clearly the dominating factor. But if m grows very large, then this part can start to become bigger because tau is fixed. And these are just some high-level reasonable numbers. So for example, let's say your bandwidth was 12.5 gigabytes per second, and so this is how much it would take you to. This is how much time it takes to send 1 byte. That's 0.08 nanoseconds. For 1 word, you just multiply that by 4. The word is 4 bytes, and then yeah. So to compare, a normal clock, like a normal machine, could have like 3 gigahertz clock. That's 1/3 of a nanosecond. And yeah, so the relationship between tau, mu, and 1. So like mu is probably 1 to 10 times the compute factor, and tau is like 100 to 10,000 times. Yeah, and this is the last slide. So to recap, the goal of designing parallel algorithms is to achieve work efficiency, or asymptotically equal work to the serial algorithm. And parallel speedup may not be limited by the number of processors, it may be limited by the interconnect. And so sometimes you can get better speedup by coarsening your parallelism, which means doing more local work, even though that seems a bit counterintuitive because you're using fewer processors. But sometimes using more processors is worse for speedup because of communication. Yeah, thank you.